Okay, so today we're going to be doing lesson 19A, which is piecewise functions. Okay, so let's talk about what a piecewise function is. A piecewise function is a function that is made up of distinct pieces with a specific domain restriction assigned to each piece. There will be two or more different functions graphed on the same coordinate plane. All piecewise functions will pass the vertical line test. Very good. Everybody remember what the vertical line test is? Yes. So if it's a function, if you draw a vertical line anywhere on that graph, it's only going to touch 1 point maximum, okay? Domain and range restrictions are represented using interval notation and unions as required. Domain restrictions, reminders, a closed circle indicates a less than or equal to or a greater than or equal to sign. Functions, pieces that belong to that specific graph, and open circles represent boundaries. So think of it as your neighbor's house and your house next door to each other, and they have a fence. Your house, your property is all the way up to that fence, but they own the boundary. They're like the closed circle, you're the open circle. So all the way close to it, you own all that until we get to the fence. Does that make sense? Yes.
Technically for the vertical line test, like if we were to do it through like x equals 0, because it's open.
Good question. Open circles don't affect the vertical line test because their boundary is not actually solid. But good question. Anybody else have any other questions like that? Okay. We're good. All right, let's talk about reading a piecewise function. So given a piece of a function, indicate the domain and the range in interval notation. So if we look at this first piecewise function here, we have to identify the domain and range. So domain is like reading the function from left to right. So if I'm looking from the left here, this function has an arrowhead, which indicates this really means it's going on forever in that direction, and it's going on forever in this direction. So if we imagine that this function is going on forever in both directions, it's eventually going to take on every x value, right? Which means that my domain is from very good. Negative infinity to positive infinity. And you also want to look for any domain gaps. In this case, we don't have a domain gap because see how we leave off at -1 here, but the other one picks up right where this one leaves off? That means we don't have a domain gap. Now, range gaps are a bit more common in piecewise functions, so let's see if we have one here. So range is from below to above. So if this function's going down, turn my volume off, getting 800 emails. So, if this function is going from coming up from the bottom and going up, it stops at what y value right here?
-3.
Good, -3. So it goes from negative infinity to -3.
But shouldn't it be bracketed?
Not bracketed because it's an open circle.
Then why don't we bracket the other one?
We never bracket on an infinity symbol. And we sometimes bracket on numbers, depending on if there's an open or closed circle or a hard boundary there. So, the problem is with the range is, see this is what is called a range gap. Does everybody see this range gap right here? So the function's coming up, and then it picks back up again. So that's where we include a union symbol. And then the range picks back up at what value? Y equals 2, and then it stops at what value?
Positive.
Good, and that 2 is going to be a square bracket. I kind of didn't draw it that well, so let me rewrite it. It's going to be a square bracket because this is a solid circle, okay? So does everyone understand how I was able to come up with that? Cool, let's move on then. So now we're going to move into the next one. This is a 3-piece piecewise function comprised of a piece of a parabola, a piece of a constant function, and a piece of a linear function. So the first thing we want to look at for our domain is if this function was going on in both directions forever, if there's arrowheads, what's going to happen? Well, eventually this function is going to end up taking on every x. So it's from negative infinity to positive infinity. Now note here that we're going to look for any domain gaps that occur here, but as you can see, every time that we stop at an x, the other one picks up where the other one left off, which still makes it go from negative infinity to positive infinity. Now we're going to look at the range. What's the lowest y value this function will ever take?
0.
Good. And 0 is included because lines and hard, like filled in circles are hard boundaries, okay? And those are not like open circles, they are included. From here, we don't have any gaps because this part of the function alone goes straight up to positive infinity. So as long as one piece of the function is continuously going up or down and there's no gaps, you can say that we don't have to worry about the union. So is everyone good with that part of the problem? Okay. So given the piecewise functions, identify the domain restrictions and then the overall domain and range. So we're going to do the specific pieces and then we're going to do the whole thing together. So be very careful because they won't always put this in chronological order, and they do this intentionally to make sure you interpret the graph correctly. So on the first one, I see that this first function has a y-intercept of what?
4.
Good. So which of these two graph pieces is going to correspond with that? The top or the bottom?
The bottom.
Very good, the bottom. So this bottom graph, we're going to look at its domain. It starts at domain, not range. Starts at
0.
0 and goes to
-5. Or 4.
6.
What?
X values only.
Oh.
So it goes from 0 to 6. Now take a look at the way I use the inequality symbols. Does everyone understand why I use the equal to for the first one and the non-equal to for the second?
Yes.
So look at the graph for a second. What do you think corresponds to it? The circles. See how the filled in circles go with the equal to and the non-filled in circles go with the without the equal to sign. Does everyone see that? Okay. So let's go ahead and try the next one. So the next one is this piece, and what x values does this function span?
0 to -6.
Good. And we always go left to right, so we're going to go -6 to 0. So remember, this only ever talks about x values. We never care about the y values with these, okay, just the x. And that's the same for the domain. The range is the only time that we're really addressing the y values here. Most of the time we're talking about x. So now we're going to talk about our domain, our entire domain. Now this function is finite. Does anybody know why I would call it finite? Good. It doesn't go on forever. There's no arrowheads indicating it's going on forever, so this is a bound function. And it's bound between, its domain is bound between these two imaginary vertical lines. Yes?
So wouldn't it just be -6 and 6?
Very good. It would be from -6 to 6. And be careful because this -6 right here has a closed bracket because of the circle, and the regular +6 has a curved bracket because of the open circle here on the other side. All right, let's talk about the range. So range is where it's bound from bottom to top. Once again, it's bound on these two imaginary lines, and it's bound from what value to what value?
-4 to 2.
Good, -4. Not 2, but what's the highest this function goes?
2.
No, it goes higher. It goes to 4, doesn't it?
What? Oh, because that's the end of the line, not the.
Yes. And they're both closed brackets because the circles are both closed on both of those.
I will say it makes me very happy that both of them are the same digits.
It's kind of nice. It kind of feels like a nice closing.
It does.
Unfortunately, they're not all like that, though. But at least we had one. Okay. So does anyone remember from 1.9 what we call this type of piecewise function? It's a special type. You're close. It's just called a step. Yeah, you're on the right track, though. That was a good guess. So this is what we call a step function. Are you all in the back paying attention? Okay.
Yes.
Okay. So we got open seats up front, too, if it isn't working out for you. Okay. So these right here, this is what we call a step function. And a step function is a special type of piecewise function that particularly deals with constant function pieces. Constant functions are just perfectly vertical functions. So we're going to identify them and identify their boundaries. So this one right here is the one that corresponds with the 3. Does everyone see why? Its y value is at 3. You see that? If that helps. So these right here correspond to the y value when it's a constant function, and we're going to look at what x values they span. So what x value does this one span? How far from the x's does it span?
-1 to -3.
Very good. -3 to -1. And keep in mind that the -3 is closed and the 1 is open, so that's why we use the inequality signs we used here.
Ms. Russell,
Yes.
why did we use x values for number 3 and y values for 4?
What do you mean number 3 and number 4?
Like for the problem that we did previous, we used the x values.
We didn't use the x values to identify. We used the x values the same way we did here. So this is the function itself. So this function was already graphed for us. So I was just showing you the graph portion of it uses the y. The actual domain on both of these still depends heavily on the x values. Okay, it's just based on the graph itself. So on this one here, this one's at -1, right? Does everybody see that? So that's this one here. And then what x values is it bound between?
-1 and 1.
Very good. -1 and 1. Be careful what inequality signs you use.
Also,
Yes.
is the 1 on the first one with the 3, with the -3, is that, no, not the
Oh.
but like the first one?
It should be negative.
Okay, cool.
Yep. I realized it right as you said it. Thank you for that.
Yeah.
And then this one's at -5, and this one's between what two x values?
1 and 3.
Good, 1 and 3. And then the 3 is not included, so we use no equals to underneath our inequality. Now we're going to look at its entire domain. So basically this is where you look at the whole thing as one big piece instead of individual pieces to identify its domain. So we look at how far it goes to the left and how far it goes to the right. So in this case, how far to the left does this one go?
-3.
Good. -3 to +3.
This is relatively easy.
Right? Not
Does
so
it
bad.
get harder?
Not really. Not really.
And then -3?
There's some that require a little more steps.
3 and -5.
Good. So the range is going to be from, good, -5 to 3. And notice that we use square brackets on the ranges. Does everyone understand why?
Because they're both endpoints.
So see how here we have both an open and a closed circle on the same line?
Yeah.
As long as there's at least one closed circle or a line itself, that overrides the open circle. Okay? The only time we use a curved bracket is if there is only an open circle at that value. Does that make sense?
Yes.
Okay. So is everyone good with that?
Yeah.
Mm-hmm. So we've been working our way up to graphing them. We've done this before in this class, so it's not the first time. But I'm gonna teach you like you've never done it before, just in case. So looking at this right away, and this is the level that I want you all, or you're striving to get to in this class. When I see 3 pieces of functions, you should know what type of functions those are. This one right here is a, starts with a C, constant. Yeah, you're right, you're on the right track. A step function is made up of constant functions. This is a linear function, and this one is another constant, okay? So constant functions are just numbers. Linear functions have an x with a power of 1. So that's how you identify those. So the constant pieces are just going to be flat, and then the other one here is going to have a slant of some sort due to its slope and y-intercept. So let's graph this one first. -1 is the y value. Okay, this is the part that does correspond with the y, and that's at -1. So that's going to be somewhere here, but it's only going to be, it's going to be a, basically, if I were to just graph this regular function, -1, it would be like a horizontal line right here. But it's the same thing, but it's only between this boundary here that it exists, okay? So it's like that everywhere that x is less than -5. So let's find -5. 1, 2, 3, 4, 5. So basically from -5 and anywhere less than -5, that's the line. Now if it's less than -5, which way am I going to do my arrow?
The left.
Good, to the left. Okay, so now we're going to move on to the next one here. So this function is a linear function. So the first thing I want you to identify if you're dealing with graphing a linear function is within this domain, does 0 exist in this domain right here they gave us?
No.
Yes, it does. 0 is
Oh,
0 is
-5. Why did I think it was
positive
1,
5.
I was
Yeah.
like,
No, I almost did the same thing at first, but yeah, so -5 to 1, 0 does exist, so we can graph our y-intercept, right? And what's the y-intercept of this graph going to be? -3. So I'm going to graph my y-intercept at -3.
wait, where did you get the -x?
I haven't dealt with it yet. I just graphed the y-intercept at -3. So it's like graphing a normal graph, but it's just like only little pieces of it. That's why we only want to graph the pieces that are within its domain. So from here, what's the slope of this equation? -1. So it's going to go down 1 and over 1, right? But this is going to be an open circle because that's at 1, which is not included. Now the issue is the rest of the values are all less than 0, right? -1, -2, -3, and so on. So I'm going to have to work backwards by going up and over to continue the rest of my line. So in Algebra 1, we often avoid going backwards with students because we don't want to confuse anybody with the slope, but in this class you definitely do need to be able to do that. And I have an open circle at the -5 because it is not included. I'm going to connect those lines, and it's basically as if we graphed the equation y equals -x minus 3, but we only look at a little piece of it. So the last one is going to be another step function. So that step function is going to exist at y equals 6, and it's going to exist only where x is greater than 1. So we find y of 6, 1, 2, 3, 4, 5, 6. At 1, it's going to be closed. And then which way is the arrow going to go if it's greater than? Very good, to the right.
So that's how your lines are so perfect. You use artificial lines.
I do, but I can do it pretty good without it. Sometimes.
I was just about to say, what the heck is that?
Sometimes. It's hard to do with this pen, I'm telling you. That was pretty good.
That was pretty solid.
That was pretty solid.
I could never.
See? I'll let you try this at the end of class if you want. Okay, so let's talk about domain and range. So in this case, let's see if our domain has any gaps. So it's coming from -infinity, it's going, and then it picks back up where it leaves off. So are there any gaps in my domain here?
No.
No gaps. Now we want to look for gaps in the range. I think there might be one. So range is from bottom to top. So does everybody see this gap that exists right here?
Yes.
In the range? So we have to be mindful of that when we go to write our range out. So what's the lowest that the range goes in this case?
-5.
I think it's -4, isn't it?
Yeah.
Oh. My
So-
apologies.
That's okay. -4, but it is a curved bracket because it's an open circle. And then that aspect of the graph goes up until we get to what? +2. But it's also a curved bracket because it's open. Union, where does the graph pick up again? 6. But it doesn't go any further than 6, does it? It just stops at 6, so it just goes 6 to 6. Close bracket.
Wait, 6 to 6?
Because see how here it just stays right at 6? It doesn't go anywhere.
Okay.
So like it's just like one little extra range value, that's it. So when that happens, that you just have one extra, you just put from 6 to 6. Yeah, there's not a great way to write that.
Oh.
Okay, you ready for the next one?
C.
Perfect. All right.
One day we should film a video where I'm you.
All right. You want to learn the lesson and teach it? You can.
I would love to.
Sounds good. Okay. So
Russell sits here and complains all the time. That's the job.
I would just ask you a million questions.
That hurts. A little offended.
In a way of like, a method of like making sure you address everything. So the first equation here is a linear function that has a y-intercept of 0. Does everyone understand why I put the plus 0 there?
So you didn't because it doesn't have no initial value.
Yeah, it doesn't have a starting value written, so when it isn't written, it's an implied 0, meaning it starts at the origin. And at the origin, it's an open circle. Does everyone know why I'm putting an open circle there?
Yeah.
Due to its boundary. Now this function has a slope of -3, right? So that means I'm going to go down 3 and over 1. But the problem is, this function only exists on the left side of the graph. Does everyone see why it only exists on the left?
Because it's less than 0.
Perfect, because it's less than 0. So I'm actually going to go up 1, 2, 3, and over to the left 1 unit. So you can always work backwards with linear functions like that. And it still makes the same form of line, right? It's still a negative sloping line.
Wait, I thought you said it wasn't allowed on the left.
What? It is allowed on the left only, not on the right.
Oh. Jeez, maybe I shouldn't.
That's okay. We all make mistakes. So the next one is a linear function with a y-intercept of what?
-1.
Good. And we're going to start at -1, and it is going to be a solid dot because on the domain, x does exist at 0, right? And then we're going to go down 1 unit and then to the right 2. Down 1 unit and to the right 2. And here I'm actually going to stop. Does everyone know what? Wait, 1, 2, 3, 4, 5, 6. Does everyone know why I had to stop there?
You ran out of
Stop
space.
at 6.
Perfect, because it stops at 6, not because I ran out of ink.
That too.
Imaginary ink, I don't. So, yes, we had to stop here because this is a bound domain, right? So it only is a little piece. So now for the next one, this one is a little bit confusing to graph because we can't just graph its y-intercept because it doesn't exist on that part of the graph. So my suggestion is to plug in its boundary. So what's 6 minus 7?
-1.
Good, so it exists right here at -1. And it's an open circle. And then its slope, what's the slope of this line? 1. So you go up 1 over 1. And it would proceed this way forever. However, we're not going to be here forever, so we're just going to put an arrow. Like that.
Did you start at 6 for that one or 7?
I started at 6 due to its boundary.
Okay.
So does anyone have any questions about the graph? Okay. So now we're going to look at its domain. So in this case, this function looks like it's going to eventually take on every x value, and there's no gaps because everywhere one function leaves, the other one picks up. So my domain is from -infinity to +infinity. Now we're going to look at our range. The range is how low the function goes to how high the function goes.
So it goes to, the highest is infinity.
Very good. The lowest is
Whatever that negative is on.
lower than -1.
-4. 5?
-4.
Well, I can't read. I can't see that well.
1, 2, 3, 4. -4 to +infinity.
Miss Russell, when you're done with this, I have a fun story for you.
Okay. I'll be waiting. We got one more slide. The other slide's pretty easy, so.
You have more?
Yeah, it's easy though. Does anyone have any questions about what we've addressed so far? All right, now we're going to go on to the part that you did on Delta Math. Does everybody remember seeing these on Delta Math?
I didn't do it. Am I gonna be behind?
No. This was Delta Math like last week. You were here. You remember how to do it?
This is easy.
Well, I'm glad to hear it.
You know what really got me? The absolute value. That is more
I
hard.
agree. I agree.
Okay.
Lesson 3,
You don't-
1.3 or whatever you had was.
Okay. All right, we don't want to hear all the complaining on the video. Then people are going to stop watching at this point. You know, we don't want
No,
to.
your viewers will think it's entertaining.
Yeah, I'm sure. Okay. So, f of 2. What that's telling me is that we have an x value of 2 and we want to find its corresponding y value. Everybody with me on this? Yes. So, what you're going to do is you're going to look at the function it's asking about and you're going to address its domain. Which of these two domain rules does 2 fall in? The first or the second?
The second.
Is 2 less than or equal to 0?
No.
No, it's greater than, so it's got to be the second one. Now, because this is just a number here, all we have to do is say f of 2 is equal to 2. Now, if it were an equation or an expression, we'd have to plug in for x and evaluate to get that value.
Wait, is that it?
That's it. So now for the next one, f of -7, that value is less than 0. So what is f of -7?
That's 2.
-2. No, sorry. 2x minus 1.
No, so all you have to look at.
Oh, we're doing that. Wait, it doesn't apply to
3.
the G one?
Not yet. We're not doing G yet.
Oh,
We
sorry.
will though. No, it's okay. Do you understand why it's 3?
No, to be honest. Oh, because you just picked the top one.
Because -7 is less than 0. I use that domain to tell me which function to use. Does that make sense?
Yes.
Okay.
Oh, I didn't realize that you're just supposed to match the set to the first letter. Oh, I jumped the gun.
Yeah, that's okay. I almost did the same thing when I made my key. Okay, so look at this one. This one's talking about h of some value. So we're going to look at the h of x function. Make sure you're matching the proper function. So h of -4. -4, which boundary does it fall on? The first or the second?
First.
It does fall in the first because -4 is less than -2. So since it falls in the first boundary, what we have to do is we have to do h of -4 is equal to, and then you're going to replace x with -4. When you do the math, that's going to come out to be -2 minus 4, which is -6.
Can you divide by 4 now, or we just leave it at that?
This is done. Yeah, you can't do anything. This is a notation. So what this means is you have a value on your coordinate plane of -4 or -6.
Okay.
That's what that notation means. So looking at the next one, g of 0, of these two boundaries, which one does 0 fall in for g of 0?
The first one.
It does fall in the first one, good. So g of
Wait,
0,
We have to write it as the coordinate?
what?
Will we have to write it as a coordinate?
Not unless I ask you to. I just wanted to explain what it meant.
Oh, okay.
If I say function notation, then no. So that's g of 0 is equal to 5.
That was easy.
Not bad, right?
Yeah, I say we drop the lesson here.
Well, I know a lot of you are going to make mistakes on the next few. So what we're going to do is I'm going to pause it. I'm going to pause my video. I'm going to give you a chance to work on it for about like 4 minutes. And then I'll put up the answers to check with me to make sure you know how to do it. Okay?
Whoa. This is the first time we're doing this.
What?
I got it right!
So check your work with the video here, with the answers revealed, and see if you made any mistakes.
Dang it, Miss Mussy, you messed me up. I read the wrong one because you were like, check the thing, and then I read G instead of F.
How did I mess you up by warning you about that? Tells you what not to do. Mess you up.